Hello and welcome, or welcome back to the GWSDAT tutorial series. Today we're going to be covering inputting and formatting data in GWSDAT. This video specifically covers the type of data, units of the data, and formatting of the data with respect to entering it into GWSDAT. See the description for videos targeting the Excel plugin and the web versions of GWSDAT. For this video, we're going to be entering data via the Excel plugin for GWSDAT. To enter data, you will need to fill in two tables, the historical monitoring data table and the well coordinates table. You can also add GIS shapefiles if you would like. The historical monitoring data table has a few fields that we'll go through now. It has the well name field. This is where you put the identifier of the well or soil boring from which the sample was collected. You need to make sure all of your well naming is consistent. For our example name here, we're going to use MW01. We have the constituent. The constituent is the name of the solute type being sampled. For example, nitrate or sulfate. Keep this naming consistent, please. The labels groundwater and NAPL, abbreviated to GW and NAPL, are keywords that can only be used for the following situations: groundwater elevation measurements with GW and NAPL measurements, aka non-aqueous phase liquids. Then we also have sample dates, which we will add for each of our samples. The date formatting is day, month, year. We have the result. For a solute, such as nitrate, we enter the result, say 5. We then choose units. The available options are milligrams per litre, micrograms per litre, or nanograms per litre. We'll use milligrams per litre. If we have a non-detect value, we enter that a slightly different way. They are either entered as less than X or ND less than X, where X is the detection limit specified by the laboratory for a specific solute. For example, if X is 100 milligrams per litre, we write ND less than 100, or we can just write less than 100 as the result. The non-detect threshold numerical value must be specified. You cannot leave X as X, and you cannot just enter ND on its own. If we're looking at groundwater data, again, we need to add our date, and then we enter the water data as an elevation above a common datum, for example, meters or feet above sea level. The units for this can either be level, millimeters, centimeters, meters, inches, or feet. And then here we write the value. In the presence of NAPL data, please ensure that the groundwater level has been corrected for the NAPL density. It's very similar again for NAPL thickness. We need to enter our date. And for each of these, obviously, we need a well name. Then we write in our value, say 5. And again, we have a very similar units to that of the groundwater, being millimeters, centimeters, meters, inches, or feet. Please ensure that a sampling date is entered, and if no NAPL is present, omit it from the table. If the NAPL thickness has been recorded in borings that do not reach the water table, the NAPL thickness should be entered as 0. On the spatial image, which will be covered in video 4.1, locations where NAPL has been recorded will be highlighted in red. Note that there is also the option to add a flag to our data. 4 flags are available to modify the way in which the data is handled by the software. EAC is used for handling electron acceptor data, not in APL. Is used for handling data which is not non-aqueous phase liquids, and redox flags can also be used which identify input data types, which are to be omitted in the event that the user activates the NAPL substitution function. Note that you only need to flag one row in the datasheet for a specific constituent X, for example nitrate, to exclude all entries for that constituent when selecting NAPL substitution. Final option is omit. which just enables you to exclude a specific row from the analysis. This omit will ignore just this row here. We'll now move to the well coordinates table. The well coordinates table stores the coordinates for each individual well or soil boring. During data analysis, these data are used to determine relative distances between the sampling locations. This means that you can use an arbitrary Cartesian coordinate system as long as the aspect ratio is 1. In other words, 1 unit on the x-axis is the same as 1 unit on the y-axis. The first piece of data to fill in is the well name. It's the identifier of the well or the soil boring, and it must be identical to the corresponding identifier in the historical monitoring data table, as the well names are the keys that link the well coordinates and historical monitoring tables together. For example, here we've used MW01, so again, write MW01. If, for example, we miscapitalize it or wrote something different, it would think this is a different well and would not correctly analyze the data. Next is the XCoord, which refers to the Cartesian x-coordinate of the sampling location, and the YCoord, which refers to the Cartesian y-coordinate of the sampling location. The Aquifer is an optional piece of data to add. The Aquifer field allows the user to associate sampling locations to a particular subsurface feature, such as specific aquifers in the event that data are available from multiple aquifers. Here you can enter the name of the aquifer up to a length of 8 characters, or you can select a letter A through G, and use B here. Note that you can use the aquifer field to spatially partition data from a large site in the event multiple unrelated plumes are present, or if wells are clustered with large gaps between them. In the case that the data was entered under an aquifer for specific well names, on initiation of the analysis, again this is covered in video 4.1, the user will be asked to select one of the unique entries, and the analysis will only consider the well names that are associated with the chosen entry. Note that the analysis associated with the particular aquifer will have the names of the aquifer appended to the title of the analysis. The coordinate units here are either in meters or in feet. And the units are used in the calculation of the plume mass balance parameters. That's the plume mass balance parameters. Finally, there are options here for the GIS ShapeFiles. It's possible to superimpose a site plan over the spatial image, refer to video 4.1. Site plans are imported into GWSDAT as shapefiles.shp files. In addition to the Excel add-in, using it implies that the only location of the main shapefile needs to be specified here. The associated data files such as .dbf, .sbn, .sbx, and .shx will be picked up automatically provided they are in the same folder. It's possible to overlay up to 7 shapefiles at once. So just find the shapefile on your computer and put the file location here. Thank you very much for watching this video. If you have any questions or any feedback, there's a link to a feedback form in the description. And if you enjoyed the video or found it useful, please feel free to like and subscribe.